All right, welcome. Okay, I've had a few students be like, where do I find the TA hours? So I've actually put a new link on the lectures for the semester and office hours. I recreated that, and then I have this new link on here for the office hours. So if you click on this will be the update of all the TA office hours. These are besides them being in lab itself. So if you have questions, you can ask in lab also. But outside of lab time, you can find the TAs in these locations during these times. So this is additional resource to be able to utilize lots of TAs, which is great. So do utilize their time. They're getting paid elsewhere. Your tuition dollars goes to pay for them. So definitely utilizing them. My office hours are also, again, Tuesday, Thursday, I'm in the Merrill Engineering Building, 2268. There's also a ECE tutoring center, so you guys from mechanical are aware more of your own ME tutoring center. So the ECE also has one that you're able to ask for questions there too. It's located on the Merrill Engineering Building on the second floor. It's down the hallway west of the advising suite, but right outside the advising suite, which is across the hallway from some of you guys' labs. It has a flyer and it says the hours that the tutors are there. The tutor will be identifiable with a little stand on their table that says ECE tutoring support on it. So that's how you know which is the tutors for those. Otherwise, you can look up the times for the TAs and they'll be in those locations, and you can then ask them if that's their name that you expect to be there. Okay, any questions about additional resources such as the tutors, office hours, and support for that? Okay, and the other thing I wanted to mention is the next exam. So exam 3 will be on March 25th, I think. Yep, March 25th. So I had a student that had a little bit of confusion, so just want to make sure that that is aware of that upcoming date for your exam 3.
Is that Thursday?
Tuesday. Yes, Tuesday. It's like pretty sure it's still Tuesday. Yep, so Tuesday, March 25th. Okay. All right, any questions about the material that we've covered so far with the Bode plots? Okay, so far we've covered understanding AC signals, understanding dB, how to convert back and forth from dB to volts per volts and back and forth. Then we went into any questions about how you now can analyze a circuit with more than one element. We've only looked at one element, but if it had more, it would be the same thing. You treat it as, or no, I guess we did do an example last time with 2 elements. So any more than one, you would you would change the capacitor over to 1/CS and the inductor over to LS, and then you're going to use the same techniques that you've already learned to be able to get an expression of V out over V in. And from there, that transfer function, you can manipulate it with algebra to get it into that standard form that you can then plot for a Bode plot. Any questions on any of those steps or concepts? Okay, so the next topic that we're going to move to is looking at, I mentioned this before, the different types of filters. We're going to go into a little bit more detail today about the filter graphs themselves, and then some characteristics about filters that are probably good to know. Then we're going to move to what's called an LC oscillator, and we're going to talk about the LC oscillator itself. Okay, so the goals today: identify the different graphs of filters, understand its terminology. The main 2 factors or terms that you're going to want to know is resonant frequency, and then AQ, which is called the quality factor. And then we're going to look at calculating resonant frequency for an LC oscillator. All right, so we're going to mainly look at passive filters. A passive filter is going to be ones that contain usually those capacitors or inductors. Once it contains an op-amp in it, you can consider that to be an active filter. So I showed you last time some examples of active filters where you just model the op-amp with like the op-amp symbol with a gain portion in it. And that would be considered an active filter. More of the others we're going to look at just are passive. Okay, so here is your low pass. So these are the magnitude Bode plots. And so frequency on the x-axis and then magnitude on the y-axis. These are in volts per volt. 1 over the square root of 2 converts into 3 dB. So that's why that one is marked there. So remember last time, so negative 3 dB. So 1 over the square root of 2 is a negative 3 dB from that. So maybe go backwards. So remember last time we talked about how for the straight line approximation, right at the frequency changes, so in this case it was here and here, right at those changes, your real graph doesn't quite go to that point. So that's where you get the straight line approximation, and then it differs by 3 dB. So when it curves to go up, it's higher by 3 dB. So instead of 20 dB, it's actually 23 dB at this point, which is going to be actually here. Oh my, there we go. So there's your 23 dB. And then when it goes from going up to flat or going back down, it's going to go below it. So it will be 3 dB less. So at 54, this is more likely going to be 51. So 3 dB less. And this one is 3 dB more. So on a linear graph, so this is what it looks like on a dB scale. And then on a linear graph, it's going to look like this one. So it actually looks more dramatic on a linear scale. So this is not in a log graph on the y-axis. So in volts per volt, you can find that point of where you consider it to not be working anymore at 1 over the square root of 2. So we consider here that anything above this level is considered passing for a high pass, and anything below that level in frequency is being passed for a low pass. So that helps define that exact point. And that will be considered your critical frequency. So those are for the low pass and the high pass. For the band pass and band reject, it's slightly different because you have two changes. You have three points of change. So the first one is your first point. The middle is going to be the location where you're trying to either get it to pass to or it rejects it at that point. So this is called your resonant frequency. So it's that middle frequency. And then the 2 on each side is the region that it will actually pass for a band pass. For the band reject, same thing, that middle frequency or resonant frequency will be the middle point of it. And then you'll have the region that it will actually be stopping the frequencies. And so you have the 2 frequencies on each side. All right, questions about the form of what these look like? Okay. So once you've graphed the magnitude plot, we can actually grab these numbers, remember, from the pole or zero locations in your what do you call that? The transfer function. So in that transfer function, when we identify those poles and zeros, those are going to be the locations of the critical frequency for a low pass and a high pass, or it will be the regions that it's going to operate in a pass band or a band reject. So once you graph it, you can look at that graph and say, oh, that is the form of a filter, this specific filter, or it's not. So it will either be a filter or it won't be a filter. All right, so the middle frequency, that omega naught, is what we consider the resonant frequency. And then we can see that the region that it actually operates in can be different. So if it's really long, remember this is a band pass. Sorry. So this is a band pass. And for a band pass, we want to pass a specific frequency. So we want it to be as narrow as possible, right? Because we want to say just let 3 hertz go through. Just let 5 hertz go through. So we don't want it to be able to say, well, if I'm trying to just pass 3 hertz, and remember that one that had all the noise on it, it will actually pass all that noise with it too if it's not right at 3 hertz. So if it's really wide and it goes, well, anything's going to pass from 1 hertz to 10 hertz, that's going to also pass a lot of that noise that we don't want. So we call that a poor or low Q selectivity. So for low Q, it's poor selectivity, and for a high value, it's high selectivity. So this Q, or quality factor, we want it to be high for a band pass. So we want it to be really narrow. And you can see that's the dark blue line there. One that's a medium is kind of red, and the one that's green is really poor. You can also, so what is this graph? Which filter type? Correct, a low pass. For the low pass, you can also have a high or a low Q. What happens here is you'll get a spike right at your critical frequency. And for the critical frequency for low and high, it is your resonant frequency. So that's why it's an omega naught again. So that makes it easy for finding the resonant frequency of a low pass or a high pass. It's just that critical frequency, the one critical frequency. So with a high Q, you can see you get a really big spike there at that critical frequency. Do you think this is a good or bad thing for a low pass filter? What would be ideal? A low Q or a high Q? The low Q. So you would want a low Q for this one. So desire the low Q. What is this graph here? Correct, it's a high pass. Heard somebody say it. Do you think you want a high or a low Q here? Ideally, the green is like the ideal one. Still low. So you want weak resonance. So what happens is in the time domain with a high Q, you get a lot of oscillations before it kind of settles. So you guys have probably seen that from, I don't know which class you would have seen that in. Physics, at least, you see that, once you have some resonance on there, it will oscillate till it will flatten out. So that's what also this means in the time domain is when you have a high Q, that right around that critical frequency, you're going to get a lot of oscillations. And so you don't really want that. So for a high and a low pass, you typically want a low Q on them. All right, what is this one? Correct, band reject. And what do you think would be more optimal for this one, a high or a low Q? Correct. You would want a high Q so that it's very selective of which frequency it's going to actually reject there. So here you desire a high Q. All right, questions on this? So we've now gone over the terminology of resonant frequency and Q factor. So those are the two terms you'll want to take away, and then being able to identify what kind of a filter type we have. Okay? Any questions on those? Okay, great. Okay. The other thing about resonant frequency is that means that your input impedance is purely real. So when you have a really high resonant frequency, then you have a capacitor and an inductor in there too. So you know that that's going to be affecting that resonance. So one other thing you can do here is that you may still have capacitors and inductors. And what they can actually do is cancel each other out. So remember, the inductor is a positive value, a positive LS, and an inductor is a negative 1 over CS. Or 1 over CS, where when you substitute, let me write this out. Okay, 1 over CS, and this is SL. So substituting in J omega L, 1 over J omega C. Remember, 1 over J becomes a negative number. So this can actually be written as minus J over omega C. And then this will be a positive value, and then you can get a negative value from the capacitance, and you can actually equate those values to be the same in value because you would be at the same frequency, and then you can choose the value of capacitance and inductance so that those would cancel out. So this would give you it would look like a purely real effect at the resonant frequency. Does that make sense? Okay. So we're going to use that when we look at the LC behavior. Okay, I do want to take another second to talk about remember, again, we went through like these different bands that you have to be like working in for very specific applications. So one other thing you can do is actually combine different filters to tune a specific pass band to be very, very narrow. So this ends up getting very complicated, as you can see, 2 different filters. But you can use it to tune to get a very, very specific range in those ranges I just said. So in this case, you would design a high-pass filter and a low-pass filter for very specific frequencies. They're a little easier to design because you only have one capacitor for each one. So it's an easier design, but it's a more complicated circuit overall. So there is an easier way than having these 2 different filters that will give us this little pass band, and that's where we get to the LC oscillator. So to get there, we need to first understand how a battery and a capacitor kind of charges up and looks like. So say we have a battery with a capacitor. I think this one's a little easier to understand, where when I put on a 10-volt battery to a capacitor that I just took out of a drawer, it starts to charge up on this side, and then the negatives will accumulate until you get no more accumulation, and then it stays fixed at that as long as you have the 10-volt battery on there. So this kind of ramps up to that 10 volts in that exponential form that we saw before. So we get this kind of ramp up until, and then it can just be at 10 volts for the rest of the time unless we take it off. So if we add in a switch here instead, and we open and close the switch, we can actually create a discharge and then a charge again and then a discharge, and it can continue on with that as much as I'm opening and closing the switch. So for an inductor and a capacitor, what happens if we have them charged and then we actually put the two of them together? You'll start to get that charge of the plus and the minus on the capacitor, and that will create a current flow because you have a plus and a minus charged differently. So as that current flows, the inductor field actually starts to become bigger. So we get this creation of current flow from the capacitor that's charged, and then it will start to create more of a field until there's no more charge on the capacitor, and so the capacitor is pretty much discharged. And now the inductor has as much charge as it's going to get, and energy. If you want to think about it, maybe energy is a better word to use. So energy is created by the inductor, and then I like to think of charge from the capacitor. So now there's nothing else creating that change in electric field because there's no more change over time. And so this becomes more of a forced current. And it's forcing the current, forces current. And it forces the current to still continue to flow. As it goes by the capacitor, it now is going to start charging up the bottom side of the capacitor, and it will have the positive charges start charging up from that current flow and the movement of electrons, and negative. And now our current starts to change, and our current is going to start going the other way. It creates that electric field around the current in the opposite direction now, until it's fully charged, and now it's going to do the same process again, but reversed. So it's basically moving the energy from the capacitor through the inductor until the inductor is fully charged, and then the inductor switches the direction of the current, and the charge goes onto that capacitor again. So it's basically oscillating the charges and the energy from the capacitor to the oscillator and back and forth. So it's kind of a cool little circuit. Over time, it kind of looks like this. So your charge on your capacitor, this would be your 0.1 that I had up here. Get them here. This would be your 0.1. Until it's fully discharged, I set at 2, and then it starts to reverse itself at 3 until it's fully at its max at 4, and then it repeats the process again. So it keeps going on this oscillation. For the current flow, the current starts off as positive, meaning I go in the direction that blue arrow is first on 1. So it kind of is positive a view of it. And then it gets its max at 2. And then it switches direction and starts to go down at 3 until it's back to kind of that beginning state at 4. And then it's going to reverse itself again and keep oscillating up and down. So it kind of looks like this. So you can see currents flowing in one direction, and then it changes and flows in the other direction. And then you can see the charges on the capacitor, so they go slowly and then until it's fully charged, and then it gets fully depleted, and then fully charged, fully depleted, but it keeps alternating the plus and the minus on each side of it. And then the same thing with the direction of the electric field for the inductor. Because of the movement of the current, it will create that, or because of the charges create the current flow, it creates that electromagnetic field, and then the fields keep changing too. Okay? Yes?
With the graph up above, where you showed the inductance over time, I wasn't sure if it was the inductance or not. Is that like the charge in the inductor, or is that like?
So this is the charge on the capacitor,
Mm-hmm.
and then this is the current flow through the inductor.
The current through.
Yeah, so this is the current flow through inductor. I'll put through inductor, if I can write through inductor. Okay, any other questions? Yes?
Can you go back up to the graph with the capacitor and battery? Just with the time graph?
This one?
Yeah, I just wanted to.
So this is kind of like a charging. So this is a switch closed. And this is when the switch is open, it discharges. And then once it gets flipped again, it will be closed again. So you can actually get this oscillation just from opening and closing the switch. Is that what you wanted?
Yes.
Okay, yes.
How is the time constant calculated just if there's not a resistor in that circuit?
So it's harder to do the time constant, so you can't use that technique to actually solve for it because we don't have a time constant. Physically, there will be what's called a parasitic effect where the wires themselves have some resistance to them, but it will be really small. So when an RC is with a really small value is going to be really, really quick. So it will charge and discharge really quickly. But it's hard to model that when you don't know what is even the parasitic of it. So we usually don't analyze it the same way we did with the general form equation. So that's why I'm talking about like what is actually happening physically when you don't have a resistor in there now. Okay, so when we have this, we can think of the capacitor and inductor in series. We're going to look at this in the time domain. Say we have some AC current. And we define the voltage of the capacitor and the voltage of the inductor. And we know that I of t is a sinusoid. So we have a peak value to it, a amplitude, and cosine omega t. We know that the voltage across the inductor can be differentiated. And the derivative of this will give me a sine, and this becomes a minus omega sine omega t. And now we can say that this, the voltage on the inductor lags by 90 degrees. So anybody remember the property of cosine to sine? Does that look familiar? So we look at this and compare the cosines and we say like, oh yeah, the voltage at the inductor is a sine now instead of a cosine, so it lags by minus 90 degrees. For the capacitor, we know that the capacitor was equal to let's see. I is equal to C dV dt, capacitance. So if we integrate this, we know that VC is going to be 1 over C, and then we have to integrate the IC, which is the I peak, and integrate the cosine. And this becomes I peak over CW. So for this one, we say that VC leads by 90 degrees. So inductors usually create a lag in your output, and your capacitor usually is what is called leading your input. Okay. So we talked about wanting to find that resonant frequency. So for this one in particular, we know that these two equations are equal because we know that, or not equal. We want to put that the voltage at, let me go backwards. So the resonant frequency, we want to cancel out these two. So we want to have VL and VC to equal 0. My L and C look the same. So in order to do that, we'll just add them together. And solve for omega naught. So this would be omega naught when they actually cancel out. Okay, these are CW. There we go. All right, so sine omega, so we can pull out I peak sine omega t. And then we can divide this 0 by I peak sine omega t, and that's still going to be 0. And so moving over one of these to the other side, this would become a positive, and this would become this, and then we would have omega naught squared is equal to 1 over c. And to get rid of the squared, we could do a square root. So omega naught is equal to the square root of 1 over LC. So this would be our resonant frequency. When 1 over the square root of LC. So if we just know the inductor value, the capacitance value, we can find the resonant frequency for this circuit.
that work if you were to find like the equivalent inductance and capacitance to it? If you had like multiple inductors and capacitors, or would you?
Uh-huh.
You see that? Okay.
Yep. So remember, the root is when you have 0. So when your quantity becomes 0. So that's also the same kind of idea, is that we're taking these components and we're actually canceling them out to be 0. And so that root of the system is the same thing as a resonant frequency. So I think I'm going to skip the steps of showing this in the frequency domain, because we can do the same thing of 1 over CS and LS. Trying to think if it really is going to show you any different. So I'll include it in my notes. Let's see, go down to that one. Go back here. But I don't feel like it's going to really add much for me to go through the derivation of that. Okay, so this is the derivation of just putting C as 1 over CS and L as LS, and then doing the same idea of creating just making sure they cancel out each other, and then you end up with the same omega naught is 1 over square root of LC. So we're going to move to the next example. Okay, so when we do, like, looking at these, we're going to go through now the process of changing these over, going through and then getting the transfer function, and then looking at the Bode plot to see the change of the output over the input with frequency. So take a minute to convert this and find the output, which is V out over V in. Include the R load in that calculation for V out over V in. So try and get a transfer function equation for this. Yeah. So find an equation for V out, and then divide your V in for
So, consider the out the same as cross resistors.
which is in parallel.
Yeah, so, resist, like, cross that resistance, and then just divide that by the that's just how it is.
So just write the equation for V out equals the expression in terms of
No, I think it's a one by so are you keeping your ordinance up to scratching out like you were before.
Yeah, over here.
It's not even their house. They're just making
How do you start?
Okay, a hint. Does this circuit look familiar? Does that help?
A little bit.
Oh. I captured it out. There we go. So if you put L and C together, you can make a Z equivalent, which is the same. It's a complex impedance, so it would be treated like a resistance. And then R equivalent can be made into is a resistance. It's the two in parallel. And then hopefully you see it as can be a voltage divider. Does that help?
What are you trying to say? You treat it like a resistance. So we're to repeat it. You combine So what was the
I didn't think this was going to stump you guys as much. Okay, so this will be LS, and this will be 1 over CS. Our equivalent will be these two in parallel. So that one's a little bit easier. So our equivalent 1 over 60 plus 1 over 500. I don't have a number for that. And then your equation is going to be V out is equal to the R equivalent times V in over R equivalent plus LS plus 1 over CS. To get V out over V in, you just take the V in and then you multiply it out to this side. So this would be an expression, but it's not in the standard form. So we would want to get rid of this on the bottom by multiplying the top and bottom by that. So that would give you, a multiplication of 1. So doing this, then I have R equivalent C times S all over R equivalent CS plus LCS squared plus 1. So I personally don't want to do this by hand, so I would go to something. You can use tab go. Okay, that's really bizarre. So you can use MATLAB. You could use Wolfram Alpha. I like MATLAB better for these, but it's going to take me a minute to get that going. So this is my MATLAB code. Maybe it's not letting me copy it. It's not letting me copy it. Okay. So from that, I just defined my L, which was 50 micro, or 50 milli, so 50 times 10 to the minus 3. Then I put my C value, my R value, my RL, and then in MATLAB, you can do this symbolic S, or not symbolic, but S, and you use TF to say that it's a transfer function variable. So this is how in MATLAB you would say this is a transfer function variable S. If you use MATLAB, make sure that you have loaded a control toolbox. And then you can use just the function Bodhi, which is really nice. So define my variables L, C, R, and RL. and then define my variable transfer function variable s, and then R equivalent, and then my h I just plug in. So R equivalent times C times S over 1 plus LC S squared plus R equivalent CS. Then from there I can plot it, just Bode of H, and then it will let me graph that. So just ignore the rest of this. Oh well, actually, so I changed my load and then graphed it also to give you a visual of the different changes. So with this, I can look on the graph and I can go to the point where the omega naught is. And in this case, it was 1.29 times 10 to the 4th radians per second. So this would be how I could find the value on the graph for omega naught. These are what the loads look like. For a load of 4, is that a high Q or a low Q? Right, it's a very narrow band. For the load of 500, it's a Q of 12. So it's anyway, that's a Q of 12. So the lower the load, the better quality factor you get here. What is this one? What filter type is this? Correct, a band pass. Maybe I didn't. 2.9. Okay, questions? Yes.
How is this going to be like on an exam? Like, how are we going to be tested on this?
So I may show you Bode plots and say what kind of filter is this.
Okay.
So be able to identify the filter. Also, if it's clearly, so one, you have to understand how to identify the filter, yes. So filter from this Bode plot, being able to create the transfer function. So, yes, you have to do some algebra in here. So being able to write this transfer function. From a Bode plot, also being able to identify where the critical frequency is or that resonant frequency. So given this one, you would say like this midpoint, and whatever that value is would be your resonant frequency. F naught, yeah. So from, it is, yeah. It's just in hertz. So this is in hertz versus radians per second. So that's the difference. So being able to identify this information from a Bode plot, being able to graph a simpler Bode plot would be another one that I could ask you to do. Is that clear, what I would expect from these? Also being able to say if you had two, does it have a high Q or a low Q? All right, this is another circuit you may see. This LC that we talked about is called a tank circuit. And what this circuit does is actually creates a sinusoidal function. So what is happening here is that, remember, this LC keeps changing the current flow. So at one point in time, it's going to go in one way, and then in the other, it's going to go the other way. If I'm looking at the voltage across them, I'm going to have a plus and a minus going on at both times. So at this node V1, it will actually look like an oscillation in voltage. So it will look like a sinusoid. So this is my V1. Do it in purple. So at this wire, that tank circuit actually creates this sinusoid, yes.
What's the name of this circuit again?
So this is just called a tank circuit. And it can create a sinusoidal function from it. So at V2, notice that this is not negative feedback. So we talked about only the other ones were only with negative feedback. So this is not going to fall into that case. So what happens here is it does a comparison between the plus and the minus and acts as a comparator. So what happens at V2? Or what do you think happens at V2 then? When V1 is positive, what's the output? The plus side's going to be greater than ground, right? So what do you get out? You get out whatever the power supply is till it hits 0. And then when it goes negative at the positive terminal, it will be less than ground, so it goes to the low value. And then we'll just keep oscillating like that. So we call this it just can create the sinusoidal function or a square wave. So either a square wave or just the tank itself, the resonant tank circuit will give you a sinusoid. So you can get both a sinusoid out of here by measuring V1, and then you can get a square wave out by measuring V2. So the function generators that you've seen in the lab very commonly just has this circuit in it. All right, any questions? Do you guys want to be done early again? Okay. All right.